Hi, this is Dr. Srikat Mumbai. Under Basic Physics course for Diploma Engineering, in this video we will discuss optical lenses. It is under submodule 4.3 under the unit 4 of light. Objectives: after completing this module, you should be able to determine the focal length of converging and diverging lenses, apply the lens maker's equation to find parameters related to lens construction, use ray tracing techniques to construct images formed by converging and diverging lenses, find the location, nature and magnification of images formed by converging and diverging lenses. Diverging lens imaging. All images formed by diverging lenses are erect, virtual and diminished. That means diverging lens never produced real image. Images get larger as object approaches. Here the object is beyond f or focal length. So this light is falling on the diverging lens parallel to the principal axis. It is refracted along this direction, and the ray that is passing to the optical center, it is undeviated. So if we extend this ray towards the focus, then these two will intersect the point, this point, and the image will form here. So this image is virtual image and it is erected and its size is diminished. That means its height is smaller than the actual object size. Now, if the object is placed in between f and optical center, then the ray of light from this tip will move towards this and it will be refracted along this direction. Again, it will pass through the optical center along this direction. So this ray and this ray, extension of this ray will intersect at this point and the image is formed. So this image, again, it is erected, it is virtual and smaller in size. Sign convention. One of the most important part for lens formula and calculation of focal length, object distance, image distance is sign convention. Very important part is sign convention. Here this picture, suppose this is a biconvex lens. So its focuses are f1 and f2 and curvatures are radius of curvature to f1 and to f2. Now when the object is upward, it is positive, downward means negative. Direction of the incident ray direction of the incident ray, it is negative distance, and along this direction it is positive distance. For diverging ray, it is for converging ray or concave mirror or lens, anything. And it is for concave, this is for convex lens, this is for concave lens. So for concave lens, this is the negative distance as the ray is incidenting from this direction and eye is here. Now this picture will give us a good example of this one. When the convention is, when the object is positive direction, this one is plus. But ray of light, this is an eye. So ray of light is coming from direction towards the eye. So in this direction, this is negative. So we are writing here negative minus u. And here in this direction, for this convex lens, the principal focus is plus 12. And if the object is produced in this direction, this one will be plus. So in this region, it will be plus. Here it is minus if light is coming from this direction. Same thing will happen for concave lens also. The sign convention in a nutshell is, if the object is along the direction of the incident ray, then this region will be negative. That means here the object distance is, or here object distance is negative. If our eye is along the eye is here and the image is formed along this direction, then the image distance will be positive. That is, the light is coming from left to right and eye is at right. If the object is along this direction is positive and the image is upward, that means erected, then it will also be positive. That means its height will also be positive. If the image is inverted, then its height will be negative. Downward height is negative, upward height is positive. This is the sign convention in a nutshell. Analytical approach to imaging. Now, this one is U. So lens formula, this one is V. U is the image distance, V is the object distance. So lens equation is 1 by V minus 1 by U is equal to 1 by F with sign convention, considering the sign convention. And magnification is M is equal to Y dash, that means Y dash is the object height, image height, extremely sorry, this is image height, and Y is the object height, Y dash by Y. So this is equal to V by U. V is the image distance, U is the object distance. So this is a magnification. So M is equal to Y dash by Y is equal to V by U. Let us take an example. A magnifying glass consists of a converging lens of focal length 25 cm. A bug is 8 mm long and placed 15 cm from the lens. What are the nature, size and location of the image? So focal length of the magnifying converging lens is 25 cm. So F is equal to 25 cm. A bug is 8 mm long. That means Y is equal to 8 mm. And placed 15 cm from the lens. So U is equal to 15 cm. U is equal to 15 cm. Now we know the formula. This is the bug. So if we place the formula 1 by V is minus 1 by U is equal to 1 by F. So object distance is given. We have to find out image distance first. So from this formula, V is equal to U into F by U plus F. U is equal to, bug is placed here. So this is the direction, our I is here. So U is equal to, U will be minus 15 centimeter. Focal length is here, this is positive, so F is equal to 25 centimeter. Here U is equal to minus 15 centimeter plus 25 centimeter. So it becomes V is equal to minus 37.5 centimeter. The fact that V is negative means that the object is virtual on same side as object. So this object is virtual object, and this is on the same side of the object. If the object is on opposite side, or if the image is in opposite side, then it will be real image. Here it is virtual object, virtual image. Image is virtual as it is on the same side as object. This example continued. Now magnification it is given. Magnification is told. Magnification is y dash by y. So y dash by y means y dash is the image height and y is 8 mm is equal to V by U. V is, here V is, this is the V, this is the V. V is minus 37.5 cm. Already we have calculated here. Minus 37.5 centimeter, 0.5 centimeter, minus 37.5 centimeter. U is 15 centimeter. So V is this, and U is also along this direction. So this is negative, minus 15 centimeter. So this minus and minus will cancel out. So y dash become 20 millimeter. So y dash plus means it will be erected. So y dash positive means that the image is erect. It is also larger. Basically y is 8 millimeter. So y dash is 20 millimeter. So it is larger than object. Another example. What is the magnification of a diverging lens? F is minus 20 centimeter. If the object is located 35 centimeter from the center of the lens. So F is given, it is minus 20 centimeter. Object is located 35 centimeter from the center of the lens. So from this here point to here, it is 35 centimeter. So again, the formula that we will use, 1 by V minus 1 by U is equal to 1 by F. So V is equal to U into F by U plus F. Now focal length it is given minus 20 centimeter. So it is easy. Easier one, F is equal to minus 20 centimeter. U is equal to 35 centimeter. So it is again this direction. So minus 35 centimeter. By U plus F, U is minus 35 centimeter. Minus 20 centimeter, putting the values U and F. So V becomes minus 12.7 centimeter. Now what is the magnification? Magnification means y dash by y is equal to V by U. What is this V? V is negative. So minus 12.7 centimeter by U. U is minus 35 centimeter. So M becomes minus will cancel out. It will be 0.364. So the image is smaller in size. Image is smaller in size plus. This is plus. So we have got plus means it is erected. Minus means inverted. So image is erected, smaller in size. Power of lens. Power of a lens is the reciprocal of its focal length. So P is equal to 1 by F in meter. or F is equal to 1 by P. SI unit of power is diopter. Commonly it is represented by D. 1 diopter is the power of a lens whose focal length is 1 meter. The power of a convex lens is positive, and that for the concave lens is negative. If two thin lenses L1 and L2 of focal lengths f1 and f2 are placed in contact coaxially, the equivalent focal length f of the combination is given by 1 by f is equal to 1 by f1 plus 1 by f2. That means these two lenses L1 and L2 having focal lengths f1 and f2, they are in close contact, then their equivalent focal length will be 1 by f is equal to 1 by f1 plus 1 by f2. Another thing, if there are n number of lenses is contact, then this equation will be 1 by f is equal to 1 by f1 plus 1 by f2 plus 1 by f3 up to 1 by fn. This should be remembered. Any number of lenses if they are in close contact. Now, the power of the combination of these two lenses L1 and L2, P is equal to P1 plus P2. P1 means 1 by f in meter, P2 is also 1 by this. For this one will be 1 by f1, for P2 will be 1 by f2. So if the lenses are separated by distance d, suppose they are not touching each other, there is a separation of d. So this formula becomes 1 by f is equal to 1 by f1 plus 1 by f2 minus d by f1 f2, and their corresponding power P is equal to P1 plus P2 minus P1 P2 into d. So this is the power. Corrective lenses. So this is the picture of the big buildings. It is blurred to us, but when you are using some specs or glasses or corrective lenses, the picture becomes clear. So we have used this one to depict the picture. Corrective lenses are used. One of the diseases is myopia. Nearsightedness or myopia. Nearsightedness or myopia is a common vision condition in which you can see objects nearer to you clearly. That is, closer objects can be seen easily or clearly, but objects further away are blurry. This is a blurry image. This one is a clear image. So near objects are clear, but further objects are blurry. It occurs when the shape of your eye causes light rays to bend or diffract incorrectly. Focusing images in front of your retina instead of on your retina. That means the image should be focused on your retina, but it is focusing in front of your retina. So that's why you cannot see the further objects. So this is the star rays, that is parallel rays is falling. So this should be the focus here, but it is focusing here. So to correct myopia or nearsightedness, a diverging lens creates an intermediate image at a distant star at your far point so that your eye can see it even though the star is beyond your far point. So this is the diverging lens that is used, or concave lens. Now when star rays are coming, distant star is coming, then it is going around this direction. This is refracted and diverging. So if we extend, it looks like it is coming from this point. So this point is a far point. Image of distant object. Image of distant objects is produced here. So using the diverging lens, this nearsightedness can be corrected. Another one is hyperopia or far-sightedness. It is a common vision condition in which you can see distant objects clearly, but objects nearby may be blurry. That means when you are reading a paper, the words remain blurry, but distant objects, say number plates of a bus or train, it can be seen easily. The degree of your far-sightedness influences your focusing ability. To correct far-sightedness, your contact lens creates an image of a book 25 centimeter away at near point. This is 25 centimeter away at the near point, so that your far-sighted eye can see it even though the book is closer than your near point. So what happens? The focus should be on our retina, but it is producing outside this. That's why we cannot see the closer objects, but we can see the far objects. How? This is the near point. So this is the contact lens we have used. Now it becomes, after refraction, this is coming to this direction. If we extend, it is here. So to correct farsightedness, your contact lens creates an image of a book 25 centimeter away. That means the image is, this is the near point. So it is produced 25 centimeter away at a near point, so that your farsightedness eye can see it even though the book is closer than your near point. It may be more close, so it can be seen easily. So focal point of corrective lens is now here. It should be placed on the retina using this lens, so we can see the closer object clearly. That is no vision or hazy vision, no hazy vision. So closer object can be seen easily.